systems impulse voltages সব সময় আমরা তাহলে একটু দেখি পাওয়ার সিস্টেমে যে ইম্পালস ভোল্টেজটা আসে যেটা স্ট্রাকচারটা কি তাহলে আইডিয়া হবে ধরা যাক এই হচ্ছে আমার ট্রান্সমিশন লাইন এইখান থেকে ট্রান্সফরমার লাগানো আছে বুশিং দিয়ে বুশিং এর ভেতর থেকে লাইন এসে ট্রান্সফরমার ওয়াইন্ডিং হয়ে আর্থ হয়ে গেছে দিস ইজ এ বেসিক স্ট্রাকচার অফ এ ট্রান্সফরমার now when lightning strikes it may be full lightning with 1.2 microsecond 1.2 microsecond time to peak this one and time to half is 50 microsecond this is 1.2 this is a full lightning impulse but what happens if there is a flashover in bushing or say some tree is there anything some tree is there when lightning strikes some arcing take place here in that case the impulse may rise and several things may happen maybe after rising to such some voltage it chops down due to this arcing it may chop at peak it may chop at tail which is the most common it is called tail chopped impulse how does it look it rises like this some tail part is there and then suddenly chops to ground voltage now if you see what happens here a very high dVdt is produced which is very detrimental to this insulation of the transformer did you understand this point
yes sir
yes this very high rate so what we will do in laboratory we will produce this chopped impulse and see whether the insulation can withstand this chopped impulse or not if yes very good if not we will have to declare it the test has been failed but how do I create this chopped impulse so fast because now if you see in the laboratory I can generate full impulse no problem about that I can generate full impulse how I can generate by a charged capacitor and a spark gap and some wave shaping section so when spark passes here I get this impulse this can be done easily but how do I make this a chopped impulse where say this time is only 2 to 6 microsecond very fast how can I initiate this very good I can do a simple thing look here I can put a sorry, I can put a controlled gap here, air gap, with the help of rod electrode. So that when the voltage rises, due to this highly non-uniform electric field, it can break and produce the chop impulse. Exactly this thing happens in nature, but this is highly probabilistic. It may not happen in 1 in 10 shot also. So this is very unreliable method of creating chopped impulse. What I can do? I can, instead of rod electrode, I can put simple sphere gap arrangement, but the result is same. But the result will be same. This will be highly probabilistic. How do I initiate that this very at this very low time the chopping will take place? This is very difficult, and it must be highly reliable because we are doing the test in the laboratory and we don't want to falter. So I can use the same triggertron gap that I have taught. I can use the same triggertron gap arrangement, because if you see, this is the sphere gap, and if you divide the timeline, this is fictitious, this is not true, just I am getting a scale. If I divide this timeline as t1 and this t2, this is to obtain the first electron, and this time to multiply it is very short. So to reliably fire this chopped impulse, I need this initiating electron which is supplied by this transformer. But how the transformer will supply so quickly the initiating electron to fire from 2 to 6 microsecond, the initiating electron must be supplied at least say 1 to 3 microsecond. How it is possible? It cannot be possible in ordinary circuit. It is possible here in this electronic circuit. If you see, this is the circuit we want to discuss today. This is very simple. If you see the impulse generating circuit, I draw it again. I will have to draw it. Is this drawing visible to all of you, what I am telling?
Yes, sir.
Okay. So the spark takes place here, and here we get the impulse. Now what happens here? Initially the capacitor is short and initially the current flows through it like a spike. Here at the time t equal to t0, the current flows, there is a pulse type initiation here at t equal to 0. If this earthling can be considered as a shunt, I can pick this voltage out as trigger. So what happened? This trigger voltage is a reference voltage at t equal to 0, because current through capacitor is very high at the beginning, and then the impulse voltage will rise and the current will fall through the capacitor. If you see what happens, this is the impulse voltage, and the current is just the opposite. The current through the capacitor is just the opposite. The current is very high here and slowly falls. As the impulse voltage rises, the current rapidly falls. At this point, the capacitor is fully charged and the capacitor bleeds through this, the capacitor bleeds through this network. So this is the t equal to 0, I get the highest current pulse, which can be converted with the help of this earth link. Automatically acts as shunt because the current is high, and even it is in the order of say 0.2 ohm, then also it will work. This trigger is given with the help of a pulse transformer. You can see this pulse transformer. Sorry, this is the isolation transformer. From the shunt, you can see it is given to the ferrite isolation and it is fired through SCR. So at t equal to 0, SCR immediately fires and this ferrite core step up transformer fires the triggertron gap at almost what I told, that 1 to 3 microsecond within. As soon as we get the initiating electron, the main gap fires, and what happens here? Here we have the sphere with triggertron. This gap is triggertron. This is R, and so the thyristor fires this gap and the impulse was rising. The impulse was rising. Within that meantime, this gap fires so that we get the chopped impulse in the laboratory. This is the basic thing. So this is the schematic. and you will have some advantage. This is very reliable. It can be adapted over a wide range of impulse voltages. The control triggering ensures repeatable and accurate chopped impulse for laboratory testing. So this is about our second chapter. We have, if you remember, what we have read from this chapter, this is how to, what is this triggertron gap, conventional triggering circuit, disadvantages, modern triggering circuit, advantages and disadvantages, a comparative study, and then the chopped impulse and its generation in laboratory. This is the second chapter. So if you permit me, I will go into the third chapter today, which is high voltage measurement. If you tell, I will proceed.
Yes, sir.
Okay. Then let us see the third chapter. High voltage measurement technique. We have several type of measurement technique that I will show you. Measurement of, see, mainly what we measure in high voltages, we have high voltage DC measurement, we have high voltage AC measurement, we have high voltage impulse measurement. Okay, these are the main three types of measurement we will be using in high voltage. Now, how to measure direct high voltage? Series resistance microampere method, which is very standard of our voltmeter system. How it is done? We have a high voltage source, we have a very high resistance, high value then we have a microammeter. This microammeter is calibrated in kilovolt. This is the method. So this is the system which works on high voltage DC. This high voltage resistor this high voltage resistor in laboratory, it is a huge structure because it has to withstand a very high voltage. This is not a ordinary resistance. So there are construction advantages, limitations, you will read it. Then resistance potential divider. This is also same. Instead of microampere, we have another resistance. We have another resistance to divide the potential and bring it to low value. That can be read by multimeter or etc. This is another method. There are design considerations. It must have low temperature coefficient and uniform field distribution is essential. So grading rings and smooth electrode profiles are often used to distribute the potential. These things are done. creepage distance is increased so that flashover does not take place. Okay. And next, what is very important is the generating voltmeter. Now you tell me, suppose there is a plate. There is a plate which is at very high potential, say 100 kilovolt. Now, without contacting it, I bring another plate. Suppose this is DC, 100 kilovolt, it is charged. So by induction, it will have a minus charge. And since this is a DC, no current will flow. Microampere equal to 0. Only charge will be induced. But if it would have been some AC supply, then due to capacitive reactance, some current would have been flowed. How? If you see here, current through the capacitor is essentially current is dq dt, then equal to q equal to cv. What we have done up till now, we have v dc dt plus c dv dt. Q equal to cv equal to v dc dt plus c dv dt. Up to now, we have considered this capacitance is a constant parameter. So it approximately goes to C dV dt. We have solved the problem using this expression up till now. But here something it will differ. See, for DC, I have told you this is a DC measurement. Is there any dVdt in DC? There is no dVdt. So this part becomes 0. What about this part? This is also 0 if the capacitor is constant. So current will be 0. But this capacitance is not kept constant. Now comes a very, very peculiar method of construction that we will have to understand. এইবার দেখা যাক যে if the capacitance C varies between limit sinusoidally, then the generated current becomes sinusoidal. I equal to V dc dt হলে if the current কি করে এটা হবে, এইটা আগে চলে যাও কনস্ট্রাকশনটায়। What happens, the capacitor, one of the plate has the induced potential fixed plate S3, see here, and S0 and S1, S0 and S1 becomes the variable capacitance. See here how it is constructed. S1 is the mirror image of S0. Where the plate has the material, it is cut out. So when S0 and S1 is at exact overlapping position, minimum capacitance will be there, because here the plate material is there, the plate material is not there. And when by rotation it rotates where the plate area is maximum overlapping, there will be maximum capacitance. So the when it is rotated by a motor, capacitance continuously varies between 0 and Cmax. 0 is not possible, so C0 and Cmax sinusoidally. So the expression becomes C0 and C0 plus Cmax. Then as the capacitance is sinusoidally varying, the current is also sinusoidal, where Imax is V, Cm and omega is the rotational speed of capacitance. If this rotation is kept constant, then Irms is Vcm by root 2, which depends on the voltage I am going to measure and all the constant. Maximum capacitance is a constant. I will rotate the capacitance with the help of a fixed speed motor, constant speed motor, and I will get Irms proportional to V. So what is its advantage? This microampere, we can rectify the alternating current and measure this. What is the advantage? Generating voltmeters do not load the high voltage source because they operate on electrostatic principles. It is not touching. This electrode is not touching. The limitations are requires careful calibration, because which voltage corresponds to which microampere has to be carefully calibrated. So these are all the direct voltage measurement principles. One is the series resistance voltmeter, series resistance microampere meter, resistance potential divider, and this non-contact type generating, only this one is the non-contact type. It operates in air capacitance, so direct contact is not required. It has got very advantage, that is infinite impedance. Impedance is very high. Now measurement of alternating high voltage. We have, instead of resistance, we can use capacitive voltage divider. We can use C1, C2, is as you have done in our lab. This is the high voltage and this is the V out. So V out equal to high voltage into C1 by C1 plus C2. If this factor can be made 1 by 1000, then V out equal to HV by 1000. That means HV becomes volt. This unit is in volts and this unit is in kilovolt. So volt you can read by any meter, kilovolt to volt conversion. So this is the capacitive divider. You have learnt also in laboratory system. What is next? Measurement of impulse voltages. In measurement of high voltage also involves potential transformer. Since you have read it in this potential transformer CTPT in several other, so we have omitted here because you know already these things. Specialty in high voltage is measurement of impulse voltages. This is the resistive divider with oscilloscope. High voltage impulse, because resistance does not alter the wave shape or phase, we can easily use simple resistive divider and with CRO. CRO, so here the voltage is in order of kilovolt, resistive divider makes it in order of volt, and CRO reads the actual impulse wave shape. There are design requirements. Resistive divider must possess very low inductance, minimal stray capacitance, so it is very costly. High voltage measuring resistor looks like this. A capacitive impulse voltage divider, it is C1 by C2. Again, capacitive voltage divider is also existent, but the construction and field control is very important. The entire divided assembly is enclosed in metallic shield connected to ground, so that no stray capacitance can be obtained. Now it has got dynamic behavior and compensation, because due to some weather change, body capacitance, some capacitance will vary, so that it must be frequently calibrated. Before testing, we will calibrate with the help of a known voltage, calibrated voltage, and we will calibrate that. How it is calibrated? Here, suppose suppose this is in, this is say 2 volt. I have given impulse say 42.9 kilovolt. So 42.9 kilovolt corresponds to 2 volt peak. In this way, you can do this. There are advantages and limitations. You will have to read it in examination. This is a capacitor. It looks similar to resistance because all the body are made in a similar structure. Now, this is very important. Transmission line effects and reflection of wave. You have read in third year, there is the reflection of waves. To match this, the impedance should be matched, so that if I use a cable, this CRO will be in control room, and this will be in the high voltage laboratory, so that this cable and the termination resistance must have the same impedance, surge impedance, so that if surge impedance of cable equal to 50 ohm, then from the cable the termination resistance to CRO in the control room should be equal to 50 ohm. Then it will go to CRO. And if this cable is 75 ohm, it should be changed to 75 ohm. Otherwise, wave will go up to here and will reflect, and CRO will read wrong voltage. Much more voltage or much less voltage. It will not read the true voltage. So this termination is very important. So impedance matching is very important here. Now comes the peak voltmeter. You have read already in high voltage engineering. So a peak voltmeter can read the maximum value of impulse voltage. During this impulse, what happens? The capacitor charges to the peak voltage and retains the value long enough to be measured. Suppose the capacitor is charged, it is stable up to say 0.5 second. You can quickly read what is the value it is going. Sphere gap method, nothing to explain. IS 1876. You have done the experiment also in 4th year. Impulse calibration by sphere gap method. But in examination, you will have to write this thing. Suppose this is the adjustable gap. IS 1876 tells that this much of gap will give you 50% DDV at this much of voltage. So this is about impulse voltage measurement. Now comes impulse current measurement. This is very essential, important actually for examination also. Rogowski coil is nothing. If you see this construction, the main current like CT without a core. Just think of a CT without a core. And the voltage, instantaneous voltage generated is the rate of change of current with respect to time, provided there is a mutual inductance between the conductor and the coil. So this differential equation, when integrated, will give the current. Induced voltage, total voltage Vmax is given with respect to current. This part, the mutual inductance and the RC time constant, etc., are all constants. So this constant can be calibrated by giving a known time varying current. So everything must be calibrated. How do I know what is the actual dynamic R and C and M? It is impossible. So everything has to be calibrated. So this is the relation between maximum voltage and the current. So the current is measured with the help of a shunt and a meter, and you will get the what is the maximum current going through the coil. Advantage, since it has got no core, it is capable of measuring very fast impulse current. Absence of magnetic core element saturation, and it is lightweight and can be easily installed around conductors. There are limitations also. Performance of the integrator, drift or offset is very common, so it must be calibrated very frequently, and it has to be very well shielded so that the noise, because integrator has an inherent problem of integrating everything. So you have small noises, it will integrate and convert it into a large value. So it must be shielded. And there are magnetic links. This is peculiar. See, at that time there were no CRO came much later. But before, CRO was not that portable device. It was a huge structure and has to be controlled by electronic valves and etc. And what happens, suppose this is the conductor that is carrying the impulse current. Now you can divide the conductor into several inductors segments. This part is L1, this part is L1, this part is L1. So with length, the inductance increases, and if you put several magnetic materials along a definite length, what will happen? The impulse current, I impulse, will flow through this conductor, and due to different inductances, there will be different time constants, and these strips will be magnetized differently, and it will trace, and due to its retentivity, it will retain several values of magnetism, and if you plot this magnetism, you get the idea of polarity. Suppose this is positive current, the magnet is, here is plus, here is minus, and if there is a negative impulse current, automatically it will be minus, it will be plus. So you get polarity, and also you try to guess the wave shape also. Think of this as your computer hard disk. It is storing data in magnetic small strips. This is a discrete hard disk to store fast impulse current data. So these are called magnetic links. See that current is traveling, and these steel strips are high retentivity special magnetic material strips are storing the data like a hard disk. For example, I have say 50 magnetic strips arranged in a span of 100 microsecond travel. In 100 microseconds, suppose the wave travels from 0 to this point. So I will arrange 50 strips and get the data from its strips, and I get 50 data, and I plot it and get the idea of impulse current. Advantage, this is rugged structure, inexpensive, suitable for outdoor installation. They do not require electrical connection or power supply, only the main current. They can withstand very high impulse current without damage. But the limitation, exact time domain waveform, it is not possible. You can approximate, but you can think this is a very crude method, and exact data is not possible. And this is the impulse current shunt, because how to measure this very high current without inductance? I will show you. See, this is the construction. This is called squirrel cage shunt. Because of squirrel cage induction motor you have learned, I will show you how it is done. There are two sets of conductors arranged in squirrel cage. concentric to this, inside I am drawing with red, another cage is there. These are the parallel conductors. So what happens? Current enters through this and current leaves through another set. Practically, current is side by side. Current is entering through one strip. Suppose this is 1 and adjacent strip, outside strip is 2, and current enters through 1 and leaves through 2. What happens? The magnetic field produced by this 1 cancel out because the current direction is here and current direction is just in the opposite. So it eliminates the magnetic flux produced and the inductance effect. So the pure resistive shunt can be made. For impulse current, even small stray inductance in the shunt can distort the measured waveform. So it is very carefully constructed. This is the non-inductive method of squirrel cage shunt. Standard limitation is there. Shunt introduce insertion impedance in current path, but still some accuracy error, say 1% error is there. Okay. In squirrel cage configuration, multiple parallel conducting strips are arranged, as I have shown you, symmetrically around the main current path, so that this magnetic field produced by individual conductor tends to cancel each other. Okay. So there is a problem in, if this is your homework, you will try to do. This is a solved problem. Okay. So this is your third chapter. Since next Wednesday is also holiday, next week I will take you পরের সপ্তাহে কি তোমাদের ক্লাস টেস্টের সপ্তাহ নাকি? ওরে বাবা, তাহলে এই শনিবার দিন সকালে কি তোমাদের পক্ষে ক্লাস করা সম্ভব হবে? তাহলে আমি ফোর্থ চ্যাপ্টারটা পড়িয়ে দিতাম আর কি।
হ্যাঁ, একবার তাহলে গ্রুপে জিজ্ঞেস করে তাহলে আপনারা বলে দাও।
কারণ ক্লাস টেস্টের পরেই তো পরীক্ষা চলে আসবে, তাই না? নাকি দেরি আছে? হ্যাঁ, তোমাদের রাত্রিরে ক্লাস করতে অসুবিধা আছে? যদি রাত্রিরে অনলাইন হয় সেটা ভেবে দেখো।
সেই শনিবার হতে পারে,
কারণ না হলে তো সিলেবাসই শেষ করা যাবে না, আরো তো দুটো চ্যাপ্টার বাকি। আমাকে তো সেই দুটো চ্যাপ্টার পড়িয়ে দিলে সিলেবাসটা শেষ হয়ে যাবে। কি করবে বলো তাহলে? ঠিক আছে, 3টে চ্যাপ্টার পড়ানো হলো, আর দুটো চ্যাপ্টার আছে।